All right, 122 students, let me work on some more video examples for you. I told you I would do this next group of 4, so all right, let's try chapter 33, and let's look at number 33. And this one, I printed up like all the other ones, so I printed up a hard copy here of it. But it's got this device, and I like the problem because it had power in it. I kind of also liked it as a good example because it gives me a chance to talk about diodes, something we didn't really lecture in class, although we did it in lab when we built our AC to DC circuit. And so I thought this might make a good one. But note this, that on the exam, I wouldn't give you anything with diodes in it. However, I would give you something that talks about the power delivered by the circuit. So that's kind of why I picked this one, was because it was a good problem that illustrated power. It was also a good one that gave us to talk about something that's a little more advanced, but not something that would be on the exam. So keep that in mind here. So here it says, a diode is a device that allows current to be carried in only one direction, the direction indicated by the arrowhead in the circuit. So this new symbol here in purple is a diode with this little arrowhead. And again, you saw that in lab, so this isn't too big of a surprise. But dealing with it might be. But you're going to see it's not too difficult. In other words, it's just saying it is a device. It doesn't really explain how the device works. It just says it's a device that lets the current go in one way. And this little bar means it can't go the other way. So when this side goes positive, what's going to happen is current's going to come up here. It's going to hit this node. And as far as going over the top, it has no troubles because it can go through the diode. That's what the arrowhead means. And then kind of through these resistors. But current going this way is blocked. So it kind of would look then something like this. So if you had a DC circuit here, okay, where this was positive. Well, maybe I shouldn't put DC. That might confuse you. But so we'll do it here. So I had my AC. And so when this side is positive, it's kind of like this branch right here is been eliminated. That is an open circuit. It blocks the current. And this branch up at the top is just a straight wire. Now, that's not completely true. Diodes do need a little bit of energy to turn on, so they take their energy from the circuit. But for simplicity's sake, I'll just say it's like a wire. And so this is resistor R, this is 2R, this right here is an R, and that completes the circuit. And so, luckily, they gave me something very easy to work with, and I think purposely, once I do the hard step, and this would be the hard step, to realize that when current is flowing this way, this is what my circuit would look like. And you can see then when it splits right here, these two R's are in series. So these two together would be the equivalent of the 2R, which matches that 2R. And then, of course, a 2R and a 2R that are in parallel would be 1 over 2R plus 1 over 2R, which is just 1 over R, and the reciprocal is R. So when you put these three together, it's just equivalent to one resistor, at least when it's positive in that direction. And that's kind of the first step, to recognize what is this diode really doing? So again, this diode is just kind of shutting this off during this, what I'll call this half of the cycle. And so the R and the R go together, and that's 2R. Okay. Now, the other half of this AC cycle, and so let me draw AC again, but this time let me say at this moment in time, the positive is on the other side of the circuit. And so what that would mean is the current would go around and it would go through this resistor. It would also come up and go through this resistor and then angle down, but this one would block it. So no current would flow through there, but it would all then come down and recombine and go through that diode. So in other words, it would look something like this. This would be the equivalent circuit. There would be an R here. Across the upper top would be a 2R. Coming back down and joining it would be another R, because this top branch would now be blocked. That's what this diode would do. That's what that bar means. And now this branch is open. And so in this, if we make an equivalent circuit, so maybe I'll kind of mark the equivalent circuit, okay, when it was positive on this side. And this one, it's going to carry me off into the next page, because these two together are series. So it would flow through here and then down here, because it can't go that way. So that would be a 3R. Maybe I'll draw one more. I think I can fit that on the page here. And so we would have a 1R in parallel. So here's an R with a 3R. And then recombining and going through a 1R. And these two in parallel would be 1 over R plus 1 over 3R, which would be 1 over the equivalent. And so I guess a common denominator would be 3R. So across the top you would have 3 plus 1, that's a 4. 3R is equal to the equivalent, or then take the reciprocal of both sides, and you get 3/4 of an R. And so that can replace with 3/4. And then it is in series with that R. And so we can add it together and get 1 3/4. So moving on to a second page, my overall equivalent circuit then would be 1 3/4. Let me write that as 1.75 R. Okay? And I'll mark that one. So in other words, this circuit sees an equivalent resistance of an R on half the cycle where the current is going clockwise, and it sees an equivalent resistance of 1 3/4 R on the other half of the cycle when it's going the other direction. So far, I haven't done too much about the AC circuits, other than I had to realize that they have to go one way and then the other, and how do I incorporate those diodes. But now I can get to the power in a circuit. The power is then V squared over R, or IV, or I squared R. I guess actually there's a cosine phi factor that we said showed up, where phi is that inverse tangent of XL over XC over R. Although for this particular circuit, there's no inductors and a capacitor, so that's all 0, and cosine of 0 is 1. And so this power factor that I made a big deal over in the lecture, I didn't even consider it for this problem because there was no inductors or capacitors which would cause the current and voltage to be out of phase with it. And so I just kind of ignored it for this particular problem. But I'll point that out because I think in the problems coming up, I better give that some consideration. So that's kind of an important piece here. All right, so now using the symbols, and I got to come back to the reading of the problem. In terms of V and R, notice it does not say in terms of the current. So of my options here, let me not use that one or that one since they each have current in there. So I will have power as V squared over its resistance. And the only other thing I would say is this is what we derived, for a full AC circuit. So for this problem, I guess it would be 1/2 in what I would call the clockwise direction. And so when the circuit is doing this, plus a 1/2 V over R, V squared over R, when the current is going in this picture, a counterclockwise direction. All right, and that will kind of finish up the problem. So let me go to the clockwise direction. The clockwise direction, the voltage just is the V, so I can just write that as V squared. And the equivalent resistance is just the R, and so that's kind of a simple translation. The other direction, though, which is what this picture represents, would still have a V because regardless of which way the current is going, the voltage source is still going with the same magnitude here, okay? But then this resistance would be 1.75 R. And so simplifying this, I would have a V squared over R, and putting those together, I guess I would have a 0.5 from the first term, and I would add to that a 0.5 from here, but then reduced by a 1.75. And so it only adds up to 0.786 V squared over R. And so that's the average power delivered to it. And I'll just point out that if, this hadn't had the diode here, well, if this R was the same as this R, this would have came out to be a full 1, but it didn't. So it's got less currents going in this counterclockwise direction, and therefore less power. So more power going clockwise than counterclockwise, and that would be the average over one cycle. So I take the 2 half cycles and put it together there. Now, maybe one more comment is worth noting. Diode is a device as indicated. I was trying to see right here if this V, if they made it clear whether this V was the maximum or the RMS. Diode is delivered, carried in one direction. Find in terms of delta V and R. Okay. They don't make it as clear as they should be, but I will point out then that the voltages that really need to go here in this equation for power, you get average power from your RMS voltage. That's what I wanted to say. And if they mean delta V is the RMS, which I think they do, then okay, this would be 0.786 delta V squared over R. And of course, we can't get any numbers out of this because they didn't, give me any voltage or current to do. So I just got to put it in symbols. Like they say, find in terms of the average power delivered to this diode circuit. All right, well, I hope that was enlightening. Like I said, for the exam, I really want you to focus here then on the power, and I'm glad I said about the power factor that goes into there, just in case there was an inductor or a resistor. And it's just kind of a fun exercise of equivalent circuits when we throw in a diode there. So hopefully that would be somewhat kind of above the scope of this class. But that made the problem a little bit lengthy. 15 minutes, so yeah, try to keep each problem at about 15 minutes. I think that makes for good timing. All right, well, let's go on to the second one on my list. It's number 41 here. I think this is a transformer one. We haven't done one of those. Oh, yeah, good. Here it says, a transformer has N1. So let's call that the primary. So there's 350 turns in the primary and then 2,000 in the secondary. So this is what we call a step-up transformer. This is going to increase the voltage. Yeah, and we said this, that the voltage coming out of the secondary is equal to this ratio of the number of turns in the secondary compared to the primary, and then multiplied by the voltage originally of the primary. So if you have more turns in your secondary than your primary, which this one clearly does by quite a bit, you're going to step up the voltage to a higher level. So a transformer has, and then they put in some numbers, okay, and then this is the input voltage. So they say the voltage as a function of time. And they give us an amplitude, 170. So again, this sounds like the North America grid. They didn't give me a frequency, but if they're doing this, I'm going to say the frequency 60. What is the RMS voltage that is developed across the secondary? Now, again, let me point out, when we write voltage of primary and secondary, do we mean RMS or do we mean maximum? And the answer is yes, as long as you match them together. So if you start talking about the maximum voltage in the primary, that will give you the maximum voltage in the secondary. If you're talking about RMSs, it would give you RMSs. So we don't write whether it's RMS or maximum purposely so that we can, use whichever one we want to use. It's no different than when the earlier problems I was doing, we wrote this a lot. And we asked this question on the current. Are we talking about the RMS current or are we talking about the maximum? Well, as long as you match the two sides, the answer is yes. And so RMS goes with RMS and max goes with max. And so that's why we write it this way. What's interesting about this problem is they clearly have given me the maximum in the primary, but asked for the RMS in the secondary. So I do need to be a little bit careful. So why don't I start this equation thinking of it in terms of maximum? So the voltage in the secondary maximum is going to be the number of turns in the secondary, which is 2,000, divided by the number in the primary, 350, times the voltage in the primary maximum, which is the 170. All right, so grabbing a calculator here, I'll take this ratio, 2,000 divided by 350, and I will get about a 5.714. Okay, so that's the step up, and it's a step up from a maximum of 170. So this is getting to be some significantly high voltages here. And this is 971.4 volts is the maximum voltage in the secondary. And so I'm not quite what they want. They want the RMS voltage that's in the secondary. And so the RMS is the maximum reduced by the square root of 2, at least if it's sinusoidal. And I guess they don't say it's sinusoidal exactly, but I think we can fairly assume and imply that it's sinusoidal here. Okay, so I will just take that value and divide it by the square root of 2 and come up with 600, and I'll call it 87 volts. Yay! All right. And